All right. Well, thanks everybody for coming. This is some work that I'm doing with the help of a grad student, Kevin Shionalin, and then it's kind of two different projects that I've smashed together. So that's the machine learning stuff, and then Becca Jackson and this whole team down below is the Terminus team that we have some cool in-situ observations of grounding lines that I want to show you as well. And so I have some kind of standards boilerplate language in here about like why we're motivated to learn this stuff and thinking that, maybe people in the audience might still want this, but I'll go quickly through it. Sea level rise is already happening, and we can see that from the data that shows us flooding happening on sunny days on the eastern seaboard of the United States. So these are the number of days that we have flooding events happening simply because the sea level baseline is rising. And this is becoming more and more a nuisance. And so people are trying to understand what happened in the past to get at like how has sea level changed in the past. And that's what this kind of data set is typically looking at. It's the sea level budget. And so we can measure global sea level from satellite altimetry, this black line, and then we can look at all the different components that add up to that total sea level change. So the steric effect is the change in density of the ocean when we add heat to it. And then all these ocean mass terms adding melt from glaciers, from Greenland, from Antarctica, and from land water storage. If you sum all of these terms up, you get this orange line. And that is corroborated with GRACE data, which can measure mass change in the oceans. And then if you add the orange line and the steric effect, you get this additional orange line, which matches on top of our satellite altimetry record. So it's effectively closing our sea level budget and saying we know why sea level changed and what contributed to that change over the past satellite time period. But really, many of us are interested in what drives future sea level. And this is an image of the Texas Gulf Coast, which is very shallow sloped. And so very small changes in sea level have a big impact on coastal communities here in Texas, but globally as well. And so we rely on these kinds of projections. This is from the IPCC report that came out in 2021, which are driven by largely by, oh, there's someone in the chat. Oh, you can't see the slides. Can other people see the slides?
I can see
Yeah, I can see
them
the slides.
just fine. It's possible that you might need to go to the top of your Zoom screen. There's two tabs up there, one that says meeting and one that says Ginny Catania's screen. So you might have to click on the other one.
I just have one.
Sorry, not you, Ginny. Sorry, for the
Oh,
people not seeing the slides.
oh, okay.
I'd say you can keep going for now and we'll follow up in the chat.
Okay, sounds good. So the biggest uncertainty that's really driving this range of sea level that we see out to 2100 is related to emission scenarios. So it's really related to human behavior and what amount of emissions humans are going to pump out that cause changes in sea level. What was added to the last IPCC report was this dashed line, and it's dashed because we don't know exactly how to plot this line. But it's this low likelihood, high impact storyline related to ice sheet instability processes. And this was kind of considered a win by glaciologists because it allowed for adding this deep uncertainty that we have around the marine ice sheet instability and processes related to that. And so the marine ice sheet instability has been written about by many people in the 60s and 70s, and it's based on early theory that suggests that ice sheets grounded below sea level with a retrograde bed slope are more susceptible to climate perturbations. The climate perturbs the terminus and it causes a retreat that can set off a catastrophic mass loss. And that's quite different from a glacier that rests on a prograde bed slope. And so, how does this manifest for Greenland? We know that Greenland has had a lot of glacier retreat, with that retreat kind of beginning in the 70s and 80s, but then really pervasive, persistent retreat beginning in the late 1990s. And this is just an example of one glacier experiencing retreat. We also know if we look at just a subset of these glaciers here, these are some that I've been studying for a while now, that they have a consistent time period in which the retreat began. So for this region, it was around 2000, and that's pretty typical if we look around the ice sheet, that regionally glaciers are beginning their retreat at the same time. But there's a huge spread in the amount of retreat that happens. And so it suggests there's a mismatch between our understanding of how a climate perturbation is applied to a glacier system and then its response to that. And I think that this is related to little mini ice sheet instability processes that are happening for each glacier individually. And so, one big challenge we have in our field is representing the processes that I care about at the ice ocean boundary that occur on these very small scales across all these other processes that occur on a little bit larger scales to the scale of a climate model, which operates on the order of 1,000 kilometers. How do we integrate processes that we think are important on this scale in global climate models? We have to cross multiple scales and involve multiple different physics in these connections. And I'm going to show you that I think we can use AI for doing that, but it doesn't negate the need for more in situ observations at these boundaries. And so to understand what controls glacier terminus change is a really challenging problem that many of us in the field are trying to address. And it's challenging for a lot of reasons that this movie really nicely highlights. One is that it's a really dynamic and changeable environment. You can see things changing on timescales from hours to days to seasons to years and multiple years. It's also a place where there's a lot of processes happening. It's not just where the ice and the ocean are interacting, but it's where the atmosphere and the subglacial substrate are also involved, creating a whole bunch of processes that often change simultaneously and are really difficult to observe because many of them are occurring below the ocean surface. And so it's very difficult to work in this area. It's hard to get in situ observations. And so we rely on satellite data to try to infer some of these processes from space. But that said, these terminus zones for Greenland are sort of the ground zero for sea level rise because they're low lying. And so they feel the climate system more strongly than the interior. And any change that happens in the terminus region propagates farther inland. And so it's important to understand and quantify the changes here and to get at like what's really controlling them. And so what we do know is that the retreat that happened in Greenland was largely simultaneous with regional climate warming in the Arctic. So this is showing the North Atlantic heat content anomaly. And around the 1990s, we began to see this large heat anomaly of warm waters being delivered via this North Atlantic current, which snakes up onto the west coast of Greenland. And then this is a reconstruction of surface melt from an ice core showing in gray, and then different regional climate models that basically corroborate that there was this increase in atmospheric-driven surface melt that began in kind of the same time period. And so together, we think that those led to the retreat. The ocean heat in Western Greenland is delivered to the continental shelf, and then it has access to glaciers via these troughs that are carved out on the continental shelf from past glaciations. And that allows for the warm water to be delivered to the glacier terminus where it can cause enhanced melting. And so here is where we have this mixture of processes. So we have atmospheric driven warming on the surface that allows for moulins to funnel water to the base. You get a subglacial hydraulic system that allows this cold, fresh water to enter the fjord. The cold and fresh water doesn't mix well with a warm, salty ocean, and so that causes a buoyant plume to emerge. And we can see these, this is a time lapse still, but we can see them also in satellite images, these satellite plumes for many fjords. And so we know that this process is both causing the buoyant plume to rise, but as it's doing that, it's entraining this warm water at depth towards the glacier, and that enhances melt at the grounding line, which causes undercutting. And that undercutting can also lead to calving. And this is just a simple time series showing in orange is the summer times, and the plumes are visible as pink splotches. And you can see that when the plumes emerge in the summertime, that's where we have enhanced calving occurring. And so that's the Serac failure related to this undercutting because this terminus becomes less stable. This type of calving behavior is very dominant at glaciers that are well grounded. This is an elevation of this glacier and then the height above flotation. So this is a glacier that's well grounded, and it tends to have this style of calving. We see different styles of calving for glaciers that are floating. Those tend to have crevasses that form at the base of the glacier, and those crevasses can penetrate upwards, creating a flexure zone. This is an elevation model over one glacier. This profile is shown here, and you can see this kind of surface depression that's formed related to the upstream or the upward propagation of this basal crevasse. And calving happens where these flexure zones develop and eventually break off a big calving iceberg. For this style of calving, it's slightly different. These tend to be deeper glaciers. We don't see the sediment plumes as visibly, and they tend to have a calving style that allows glaciers to take these large steps backwards in time across the entire width of the glacier. And so all of this background is to suggest to you that there's multiple different processes that are occurring in the terminus zone that we all want to try to represent in ice sheet models. And currently, there are 6 leading calving laws and 2 melt laws that are used to parameterize terminus change in models, and they all represent different kinds of physical processes like flotation, crevasse penetration, stress and strain, different relationships for that, and then melting, which is largely a function of subglacial discharge and ocean thermal forcing. But I argue that all of these laws have some kind of tuning parameter that's used to predict or to best match these laws to observations. And this is an example of one where the calving rate is predicted based on the ice velocity and the measured tensile stress. And then that's divided by this variable called sigma max, which is a calibrated stress. And so essentially, sigma max is tuned for a particular glacier in order to predict a calving rate that matches observations. And this is the tuning shown for a whole suite of glaciers in Western Greenland for a study that was done by Matthew Morlham, just to show that this sigma max varies pretty considerably in a way that might be unrealistic. And so instead of trying to use these existing process-based calving and melt laws, our goal was to use just the variables alone in these laws to predict glacier retreat. And so what we did is we took variables like ice depth or ice thickness, we took ocean thermal forcing, subglacial discharge, ice velocity, and strain rate, or some version of the stress at the terminus. And we also looked at melange because there's a lot of debate in the community about the influence of melange in terms of its importance of putting a backstress on the terminus and suppressing calving. And this is one paper that demonstrated this, where they looked at sea surface temperatures. And so this is for Jakobshavn, which is located right here. This is the Jakobshavn Fjord, and this is Disco Bay area. This is all sea surface temperature from MODIS. And this box is delineating this region here, and it's showing sea surface temperature over the course of 1 year, from the summer into winter and then back into summer again. The glacier terminus is located here, and these are calving events that happen. And so you can see that when the sea surface temperatures get really low in the wintertime, that's when calving is suppressed. And so it suggests that melange presence may also have an impact on calving. And it's not yet included in any of those laws. And so we took data sets from all these different kinds of parameters and built time series out of these data sets. And so we use terminus position data that come from an automatic delineation of terminus boundaries from AutoTerm. This uses a whole composite of different satellite products in order to get a very dense, mostly seasonal from 2014 onwards, time series of terminus data for all of Greenland's glaciers. We also looked at regional climate models. This is just RACMO, but we also looked at MAR, putting out runoff or subglacial discharge estimates as time series. We got ocean thermal forcing data from Mike Wood, who wrote this paper back in 2021. These curves in the background showing this incredible seasonality is all the ocean thermal forcing data that is produced from in-situ mooring and fjord resolving models coupled to echo climate or ocean climate state estimation. And then we also get melange presence from sea surface temperature. This is a raster product. And so what we do to make a time series is we take our terminus pick and then we delineate a region, several ice thicknesses downstream of the terminus and several ice thicknesses upstream of the terminus, and we take averages of the data product within that region. So for melange presence, we simply looked at what was the average sea surface temperature within the box that's colored orange here. For ice surface elevation, we use this seasonal elevation change product that comes from Conadol. For this, we had to do this red box of looking at what's the average elevation change in the region, several ice thicknesses upstream of a terminus pick. And then the same approach for velocity data. We look at the measures product and get ice velocity that is averaged within this region. And so these regions are allowed to move as the terminus is advancing or retreating. And then also bed topography comes from bed machine, same idea. We look at what's in this red box and we build a time series of what is the terminus bed elevation and bed slope that is being experienced by the terminus position as it's moving in time. And so we build these different time series and we kind of lumped them into groups that are shown here. So geometric variables are ones that related to the geometry, the ice thickness, and slopes of the glacier, individual glaciers. The dynamic variables are the velocity and strain rate, which is derived right from the velocity product. And then the climate variables are ones like subglacial discharge, ocean thermal forcing, and melange presence. And then our goal here is to try to predict the kind of behavior that you see here. So this is echipthermia and its retreat. And then this is just the time series, all the data that we have, and we have an interpolated version of that time series. And we can deconvolve that into two different components, a long-term component and a seasonal component. And the first project I'm going to talk about is really focusing on the seasonal component. And for seasonality, we limited the study from 2000 to 2021, and that's because that's when seasonal cycles were more visible in most of the data records. We had at least 4 points per year that defined a seasonal cycle. And so there's almost 300 glaciers in Greenland, but only 115 of those had ocean thermal forcing data associated with them. And then only 46 of those had the most complete data coverage in order to do this first experiment. And I make this point because as a community, I think we spend a lot of time building these really amazing data sets that I am using for this work. And it's incredibly important that we keep maintaining these kinds of data products because they need to be improved with time so that we can cover more and more glaciers and get estimates or predictions of terminus behavior from a larger sample size. But we also need constant updating and maintenance of these kinds of data products, which is really challenging to get when our funding is being cut so dramatically. And so the goal then is to take all of these different data products as time series and predict terminus change. And so what we did, this is just one example where we allowed the model to see the data and train on the data up until 2016. And then we asked it to do a prediction from that period onwards. And so our prediction is shown in black and the actual data are in green. And so we can see for this glacier, we get a really nice match to both the seasonal amplitude of change and the timing of seasonal change as well. When we look at all the glaciers that we examined for this study, and this number just refers to the glacier ID, we find that we get pretty accurate predictions for a lot of glaciers, but the accuracy is improved when we have glaciers that are faster, deeper, have larger seasonal swings, and less long-term retreat. And so that all kind of speaks to the idea that there's like a high signal to noise ratio that allows for us to do better at predicting seasonality when it's a really big signal and the long-term change is more suppressed. For this kind of model, we can do this SHAP analysis. So it's a way that you can open up your model and inspect which parameters were relied upon for these predictions the most. And this SHAP value should add up to the total amount of terminus change observed. And so each of these bars represents a fraction of the total amount of terminus change that explains the prediction that was obtained. And we, again, color these variables by these different classes. And you can see that bed slope and surface elevation tend to be the largest parameters that are, or the parameters that are most relied upon for predicting for most of our glaciers. So we played some games with this model. This is the same plot I just showed you, but we played a game where we turned off just the geometry variables. And so things like surface elevation, bed elevation, and bed slope, we just allowed the model to not see those variables. And you can see that our prediction is muted in the amplitude. And so it doesn't do a good job when geometry is not included. But then we played the same game with climate. So these two plots are the same. And I just say, okay, now you're not going to see any climate data. And you can see that there's almost no change in our prediction. And so it suggests that climate variables aren't very important for predicting seasonal terminus change, which is kind of a ridiculous headline. I made this with ChatGPT. I thought it was funny. Because we know that glaciers are controlled by climate. We know that the whole reason we have seasonal cycles is because of climate. And so it's not reasonable to say that climate is not actually controlling these glacier termini. What we're trying to say is that the seasonal climate is controlling the initial perturbation, but geometry essentially modulates how that climate forcing is applied. And geometry is really the most important variable for accurately predicting the amount of terminus change that you would see seasonally. And that's demonstrated in this plot here. So this is identifying for all the glaciers that we looked at in this study, where did geometric variables fall in terms of importance? Was it the first, second, or third in terms of importance? And you can see that many glaciers listed geometry as being in the top 3 important variables used for prediction. But it's not so simple to say, like, you can only just use geometry to predict your terminus change, because this shows the number of variables that are needed to reach a 75% basically match to the observed terminus change. And so it says that you need between 5 and 6 variables in order to get to like 75% of the observed terminus change. So it suggests that geometry is a very key factor to controlling the magnitude of terminus change, but that retreat laws or parameterizations are going to be complex combinations of different parameters for different glaciers. Okay, so some results that have not yet been published, we're trying to get them out this summer, are related to this long-term component and trying to predict these very large long-term changes that happen. And we had to take a different approach for this kind of experiment because we can't train on this time period because there's not a long-term change that's really happening. And so instead, we built this kind of fake glacier, which consists of many glaciers stacked together. This is one glacier, Con, which is illustrated here, and its retreat is shown here. And what we did is we added many different glaciers together, normalizing all their starting points so that we could kind of build this sort of like monster glacier that experienced lots of different retreat cycles. So some haven't retreated, some retreated and then restabilized, others maybe retreated a lot more, and then some are experiencing ongoing complex retreat. This is just one example where we built a training data set out of 4 glaciers and predicted a different glacier called Ikip. And we were able to predict this long-term retreat behavior. But it took some work to find a training model that was actually a good application for many different glaciers to test. So we actually built a model on 31 glaciers, and we kind of handpicked those glaciers to be able to predict retreat behavior. And so we skewed our population more towards retreat, and we required that there was more than 10 years of a time series so that we're not capturing the time series right in the middle of the retreat that's happening. We wanted to be able to see the before the retreat, during retreat, and after retreat. So it requires, again, this like curation of very long time series data is super important to our work. So this is just one example that we have of a glacier experiencing retreat. This is the observed terminus position. We take a smooth average of this as a multi-year trend. And then this is our machine learning model prediction that is also smoothed for comparison. And so for this model in particular, we're able to predict the timing of retreat, the overall magnitude of retreat, and the restabilization of this glacier in around 2015 or so. It's not a perfect prediction, but it does a reasonably good job. When we look at our total population, this is the root mean squared error normalized against the amount of retreat that happened. And we see that we get more or less good results everywhere. The red results are ones that we discounted as poor. We find that we have improved prediction where glaciers are colder and deeper and they experience larger retreat. And that's largely because those glaciers are fitting within the training model that we built. We built a model that was skewed towards retreat, so we can do a better job when we have glaciers that are retreating a lot. The same model was used as we did for our seasonal stuff, so we could do the same experiment of opening up this model and looking at what was relied upon for the prediction. And again, we see the overall importance for geometric variables is predominant for this work as well. And so we think it's the same thing going on for this study, that this long-term retreat is is initially triggered by the climate that's happening, climate change that happened in the 1990s. But this amount of retreat, the spread and retreat, is related to heterogeneous response because of local geometry. And so this all suggests that geometry is important to terminus dynamics. And we know this is true because a study came out in 2017 that showed how if the geometry changes because of sedimentation evolving and creating new topography over time, that this can lead to advance and retreat of glaciers on reasonably long time scales. This is a model result from Doug Brinkerhoff, and it shows a glacier in cross-section. Sea level is here. This is the bedrock, and this is sediment that's being produced by this glacier through erosion and transport of that sediment in a modeled subglacial hydraulic system. And then it gets deposited at the terminus, and there's some diffusion of sediment as it's in the ocean floor and just being built up over time. And you see this interaction between the terminus position and the geometry of this moraine that it sits on. And when it gets to a point that it's on a retrograde bed slope, it shoots back, just like the little marine ice sheet instability process that we talked about earlier. And that's depicted in this terminus position going through these very slow advances and fast retreats over time. And so we wanted to try to understand this process, but particularly we wanted to go to glaciers that are currently active because there's been a lot of studies looking at paleo moraine environments, paleo glacier environments in fjords, but they didn't have the glaciological conditions that were responsible for creating those deposits at the time, right? Because we're looking at like past glaciations. And so we wanted to go to a modern environment where we could measure the different sedimentation processes we think are important and look at the rates of those sedimentation processes and try to understand how big are sedimentation rates. Can we effectively change the geometry on time scales that are relevant to the satellite era changes that we see? And so our goal was to make those measurements in a whole bunch of fjords. We managed to get to 2 different fjords. We went to a glacier that was stable, and I'll talk about these results today only. And then we also went to a glacier that's neighboring that went through a very small retreat. And we used this ship from Ireland, the RV Celtic Explorer, that provides a platform for lots of different scientific observations. And so we were able to do a lot of surface ice mapping with drones. We had seismic profiles that we could launch from the ship. So we have a nice record of the past glaciations and the seismic data. We were able to do sediment coring and a lot of oceanographic surveys as well. But the main tool that we used was this submersible called Nereid Under Ice, which was built by Woods Hole Oceanographic Institute. And this is a submersible that was built specifically to be near ice, primarily under sea ice. And it's never been used in a glacier terminus environment before. So it was a new test case for them. Nereid is capable of lots of different observations that can be tuned to the needs of the specific researcher. We were very interested in mapping both the seafloor and the terminus. And then we also put a small seismic system on board to look at sub-bottom profiles and stratigraphy of the moraine surface. We collected turbidity sensor or turbidity measurements in the water column, and then had ADCPs and temperature and salinity on NUI as well, so we could look at oceanographic properties. And NUI's a really cool instrument in that it operates in this low drag mode for transit, but then it also has a big bay that opens with an articulating arm that can be used for sampling. So this was what allowed us to get cores very close, proximal to the glacier terminus. And it's all operated on the ship with a whole team. This is the pilot, and he's literally controlling it with an Xbox controller, and it can be controlled in real time. So you can stand here and be like, oh, I want to go to this place and get this core, and he can just go and do that. But if it's connected to the ship with a tethered fiber optic cable, and if that breaks, NUI can go back to the ship on a pre-programmed path that still collects data. So it works in this ROV/AUV mode. So it's a very versatile instrument, although very expensive to use. It's very versatile for this purpose. So the data I'm going to largely show you are the stuff that's very close to the grounding line. We have multi-beam pointed towards the sea surface, the seafloor, so we could look at the seafloor topography. And then we also collected multi-beam data of the subglacier terminus face. And I'll show you that as well as some ADCP data. And so this is just a planet image of our glacier. It's about 5 kilometers wide, and the ship is actually captured in this image here for scale. This is a drone image of the terminus when we were there, and the terminus identified from the edge of that drone image. This is multi-beam sea surface, sorry, I keep saying that, sea floor topography from both the ship out here, and then NUI is this more detailed sea floor topography data. And just to show this in a little more detail, I can remove that drone surface, and you can see that NUI was able to go basically behind the terminus in sort of a map view sense. And we have a lot of evidence of sediment movement at the seafloor. And so if I zoom in on some of this, you can kind of see these channels here, and then all these bed forms that are pretty ubiquitous across the entire surface, suggesting that there's a lot of movement of sediment that's very close to the seafloor. We had multiple dives that were separated by 11 days, and so we could actually see changes over time. So this is a repeat survey in the same location showing some failure of a slope. We had this survey very close to the terminus, which is here, showing this push moraine that was developed when the terminus calved off a little bit. And then we have migration of bed forms. So I've just traced the crest of this bed form here and then just translated it to this image. And so you can see both like the morphology of the bed form is changing over time, but we're seeing this kind of upwards translating bed form migration in some regions as well. And now I'll show you some kind of merged data products. This is a movie that shows the submarine terminus face in the context of all the other data. So we have the drone data, we have the multi-beam seafloor topography data. We did 2 passes of the submarine terminus face. One was at 25 meters off the bed and one was at 100 meters off the bed. And I'm going to show you the 100 meters off the bed data set. This is just the path of NUI. So it's a point cloud that's been interpolated and then it's colored by depth. And as we zoom in, you can see all this really amazing texture of the terminus face. And this is an interpolated surface from a point cloud. So I'm going to remove that interpolated surface and just show you the point cloud. And really, I want you to understand why we clipped it and created these kind of black holes here is because there were these acoustic shadows that show up in the multi-beam data where there's some obstacle that prevents us from seeing behind it. And we think that some of these are maybe just where crevasses are located. But there's also evidence that there's a place here where there's probably a subglacial outlet, and we just could not see any returns at the back of this thing. And so to kind of focus on this outlet, we call it the cave because it looks like a cave. And for scale, I put the Statue of Liberty, sorry, it's American focus. It's about 150 meters tall and about 150 meters wide. It's very smooth surface and deeply, deeply undercut in this region. And so we think this cave is located here. These blue dots represent all the different acoustic shadows that we found in different surveys that we took with the NUI multi-beam. So there's lots of places where we think there could be either outlets, potentially where water could be emerging from the face, or they could just be shadows where we weren't able to see behind a surface like a crevasse. And so we're currently trying to provide somewhat of a trust metric on interpreting these blue dots as locations where there's subglacial water coming out. And one way to do that is looking at the subglacial hydraulic potential, which is shown here, predicted from a Polar Geospatial Center surface topography and bed machine. And it shows us that most of this is Monte Carlo based on the uncertainty on the bed topography. And it shows us like where the flow paths would be. And so when you stack them, you can see the most likely flow path, which is highlighted in yellow. So it shows that most of the water is very likely to be coming out in this region that we call the cave. We also surveyed over top the cave region with drone video, and you can see this beautiful sediment plume that was there most of the season. It's a place where there's a lot of feeding grounds. I don't know if you can see this black dot here, but that's a seal that's just hanging out in this plume because the critters at the bottom of the ocean get stunned by the cold water and they rise in the water column and it becomes a feeding ground for birds and for seals. But the place that I'm actually really excited to show you is just around the corner from our cave feature. We call this the Seep, and it's a very different region. It's a very flat terminus space. And you can also see this texture in the terminus face, this kind of vertical rilling that we thought was maybe an artifact, but I don't think it is anymore, because we actually can see these rills branching and coming together over the surface of this glacier. I don't have the data for that right now, but my student's working on that. We see this happening. And we call this the seep because we hypothesize that there's water coming out this broad, wide opening here, and simply it's leaking because it's very diffuse, leaking like sheet flow, but it eventually forms rills that allow it to diffuse up to the surface. And we found an analogy in an iceberg that had calved off while we were there. We did a drone survey of it. And so this was an iceberg that we think was the submerged terminus face that then got upturned so that we could look at it in detail. And so the basal ice is here. There's some good evidence of freeze-on for this glacier. The ice for this glacier, I think it's like 300 meters thick at the grounding line. So we captured a large fraction of the subglacial thickness or the submarine thickness. And we see the same kind of rilling pattern, these like upwards branching rills that have the same geometry and dimensions as we see in the submarine environment. And so we think that this is a place where water is probably leaking out as well. And I'm going to show you another profile from NUI that was taken even closer to the grounding line, where we were able to see into that area. And I want to show you evidence of that by kind of rotating this point cloud so you can see top down. This is the seafloor behind the seep that we're able to see. So it's good evidence that we're able to see directly into this part of the subglacial system. And so we hypothesize that this is what's called the distributed subglacial hydraulic system. And then I want to show you some kind of new ideas that we're putting together on how this distributed system interacts with the more channelized system. And that comes from ADCP data. And so this is, I'll walk you through all this. So this is the terminus position. Our cave is located here, and the seeps are just around the corner. So it's a map view. And this was ADCP data taken from Nereid. So the submersible was going along these track lines and collecting velocity data within 230 and 270 meters depth. So this is the lower 40 meters at the seafloor topography. Okay, so it's the very lowest velocity data within, and it's binned in a 40-meter average, like vertical average. And so what you see generally is that there's this movement of water, ocean water, towards the glacier with a lot of focused inflow at this cave region. And this day, August 6th, was a very sunny day. There was no clouds in the sky, very warm temperatures, lots of radiation. So we think that there's really good large melting, good assumption that there's very large melting happening during this time. And so this kind of inflow and focused inflow at the place where we think subglacial discharge is dominant is very clearly represented by this kind of classic exchange flow this idea that we have that buoyant plumes are emerging in this cave region that's causing this vigorous drawing in towards the glacier of ocean water at depth. And we have good evidence of that on this day on August 6th when it's very sunny. On a different day, same type of velocity observations. We don't have as many surveys this day, but the same depth. We see a different scenario. This day was cloudy, lower melt conditions, cooler temperatures. And instead, we see that water is more or less equally coming into the terminus face, very well distributed across the entire face. And so this suggests that during these low discharge time periods, that this classic exchange flow idea breaks down. And instead, what we see are much more distributed and more complex plume organization. And it suggests that our idea of exchange flow is really just valid when we have a certain discharge state that is the sort of classic idea of what we expect. Warm conditions, focused flow, lots of channelized discharge. But when we have those off periods, when it's not as vigorous, it actually completely turns into a different kind of regime. And so it's very dependent upon the discharge state, the subglacial discharge state. And so the important takeaways from this work are that we think glacier terminus retreat is predictable without any kind of prescribed physics, that the actual observations that go into our model encode the retreat themselves, so they can be used directly for predicting retreat. We also see lots of evidence that climate is causing the initial perturbation for glacier retreat, but geometry really mediates that response, and that helps to explain heterogeneous terminus retreat that we see around Greenland. And then we also have this great in situ, highly detailed observations that show us lots of different terminus processes that are really complex and they evolve through time. And this kind of work requires these detailed in situ observations that are really, really challenging to get. And so I want to make a plea that we can perhaps maybe work together as a community to try to build these kinds of observations more together as a community rather than through competition, because it takes a village really to get some of these really challenging observations. And so the more that we can build together as teams, the better. And with that, I am happy to take questions.
Awesome, Ginny. A great round of Zoom applause currently, and what a fantastic way to end this term's seminar series. Um, so yeah, the rest of the time until the hour, we have questions, and either just speak up or raise your hand via Zoom, and you can ask a question.
I'll just repeat one of the questions coming in from the chat. We say, is it possible that the different ocean currents are due to tidal forces?
Oh, I've looked into that. Sorry, I'm just trying to find my chat. Oh, I don't
I
remember.
know it's tough when you're sharing your screen to
I
see
think
all this
Yeah,
stuff.
I think
I
that's
guess I can
Martin's
stop it.
question.
Yeah,
Um,
that's Martin there.
there we go. So I looked into tides, and it turned out, if I can get this right, it was kind of the opposite sense. Like the tides were high during the low discharge time, and so it would have caused more focus flow. And it turned out to not. It was going in the opposite way to have tides explain what we saw. And so that's our idea, is that tides are not responsible for the shift in the sort of ocean interaction with the terminus. But you can help us by critiquing the paper when we get it out. The sediment cores, we haven't, so you can talk to, oh my gosh, I'm blanking on his name, John. Oh my God, I feel so embarrassed now. John at the University of Florida is Jaeger is the one who's doing all the sediment core information data, and they're doing a lot of they've done a lot of logging right now. I think they've interpreted some changes in sort of regime as the glacier. This one glacier has been stable via the over the satellite era, but has good evidence of being advanced during probably the last glacial maximum and the little ice age. And then there's possibly it was more retreated than it is today, and then it re-advanced. There's some evidence maybe in the cores of that and in the seismic data. But they don't have a lot that is like interpreted from the NUI cores yet. That was a whole experience, I would say, because we we had this like really dumb idea that we could see the seafloor in Nui, and there's cameras all over the place. And so we opened the bay up, and it was just like driving at night in a snowstorm. Like you couldn't see anything at all. And so that had to go out the window. And so they thought they could see the articulating arm to like get a core and put it back into the barrel, and you couldn't see anything. You couldn't even see the arm moving in front of you. And so that required a lot of re-engineering and how to get samples. And while we were testing out some of these, we were on the seafloor, and Nui was accumulating sediment unbeknownst to us because the bay was open. And we knew we couldn't lift off the ground when we were done and wanted to come back to the ship. They had to lose all the ballast in order for Nui to resurface and come back to the ship. And they gained like 50 pounds of sediment that quickly. So we have like these kind of weird ways of collecting sediment samples. I would say that it's like coarse. It's like sandy. There's sand out there and really mobile along almost entirely the entire bed is pretty mobile. And it looks like for this glacier, because it's been stable for so long, that it has, let me go back here. Let's see, I could probably do it more easily. here. So it has this channel system that really maybe
Mhm.
efficiently transports sediment away from the glacier. So it's all
Ginny,
kind of coalescing. Oh, I'm not sharing.
no.
Okay. Oh, wait. Here we go.
Yep.
Um, so all these channels coalesce to these two channels, and then off screen there's like a deeper channel. This whole basin up here has filled with sediment, so all these seem to be bypass channels, and all the sediment's mostly like just going out to a lower basin. This whole thing is just full of sediment. We don't know what this is. We don't know how to explain that. We're still trying to understand a lot of the features that we see, and there's some good analogies to some fjords in Canada that have a lot of sediment coming into them because they have glaciers that are feeding the streams. So we're using those to try to interpret some of what we're seeing. But yeah, stay tuned for sediment core information.
Any other questions? I have a
So
question, Ginny. Oh,
you go
so
ahead first, Michael.
thank you, Alan. So the iceberg from the drone footage, and because it's right above the seep, correct? But
The rills. So the
the
rills are
risk, yeah,
actually they're right above the seep, but
yeah.
now that we've found them, we see them everywhere,
Mm,
and it seems like this is like we're learning this, so it's not vetted. This is not vetted science at all.
yes.
But the terminus face, we can like see the slope of it. And
Hmm.
where the terminus is overcut, there are rills on it almost everywhere. And so we're thinking, is the distributed system everywhere? Yeah, it has to be, right? But we don't see evidence of a distributed system. We don't see the hole everywhere, but it's often blocked by sediment piled up in front of it. So on the other glacier that I did not show you data for, we found the similar thing, vertical rills over a very low, broad channel at the bottom. But often I think this distributed system is like blocked by sediment, maybe because it pushed the sediment as the glacier advanced a little bit. I don't know if that
No,
answered.
that's super cool though, because to me the iceberg didn't seem super. It was hard to tell the slope, I guess. But
Yeah,
I've thought about this at Helheim, but like it to me it's really hard to like figure out what was caused by melt and then what was caused by like the fracture if the calving event just
yeah,
cracked the ice a specific way, and then how much time does it have to melt to calving? You know what
yeah,
I mean?
yeah. This
It's
was a massive calving event, and the fracture was behind this face,
mm, yeah.
um, if that makes sense. And
No, that
we have multiple passes of the terminus in between calving events, so we probably could characterize like what the face looks like, what the texture of the face looks like after a calving event. Like
mhm,
in my mind, it might look more like something like this, where it's got like multi different faces that are all different angles from one another. But this signature to me makes me think that it's imprinting a melt pattern that must be
mhm,
persistent for some amount of time. And I did a ballpark estimate of the melt rate from looking at how much the terminus advanced in this one area where the seep is located and what the velocity of the ice was there.
mhm.
It's on the order of like half a meter per day.
Oh, wow.
So, and then there's a differential melt rate because there's more melting in the deeper part of the rill to cause the rills to even form, and that's like I think that was like another 0.05 meters per day. So a little bit more elevated in there. Is there a way to include long-term variability in your machine learning model? I would argue that that's already in there. It's like all of our data that we're using, velocity, bed change, surface elevation change, encode the long-term behavior of the glacier in this climate system. And so it's able to use that information to predict the behavior of the glacier. And it's not perfect. And I'm really here's an experiment I want to do, like end of career. I want new data products eventually that are better than what we have now. And then I want to repredict, because my guess is that our inability to predict is because we have poor data. Like we have poor ocean thermal forcing data. We don't really know melange presence is that good. It's not really the same as melange strength. I would argue our bed topography is weak at the termini. And so if we had better data, I could rerun this model and I bet you we would have better predictions. That's my guess. And then you say, I wonder what kind of attributes, complexities lead to spread among three types of glaciers. What do you mean by the three types, Mohammed?
Um, and I'm sorry, I'm probably not using the correct word.
Mm,
After your SHAP analysis, you showed that you have a spread among sort of three categories of glaciers. If you go back to like to your
yep.
SHAP analysis, and I think it was one or two slides after it. And
You
thank you for
see
the
this?
first answer. And I'm not sure what end of career is for a faculty. Uh, um,
Someday I hope to retire. Were you talking about this one?
no, so if you keep on going, actually, can you scroll up? We just went past it. Keep going up. Yeah, so this one,
This one. Okay.
yes, so geometric,
Yes.
dynamic, and climatic. So importance first, second, third. I was
Yes.
wondering about the, uh, you know, glaciers, which, what kind of, uh, is it geographical location that dictates,
Yes.
uh,
Yes. Yeah.
and
And
what
okay,
kind of
so
things?
I will point you to my student Kevin's paper that's in the cryosphere. It came out, I think it's finally published this year. And that's on the seasonal stuff. And so I'm pointing you there because I might tell you an answer that is confusing the seasonal results with our long-term results. But the idea behind this is that, yes, some glaciers choose climate variables as their most important ones, and some glaciers choose dynamic variables as their most important ones. And that was true both in this study of the seasonality, but also in the long-term study. And what we found was that, and this is where I might be getting confused, is that for the ones that choose dynamic variables to be most important, they're really fast glaciers. For glaciers that choose climate variables to be really important, I think they were very warm glaciers. And so they don't necessarily group geographically. Maybe the warm ones do, but they group more in terms of they lean on the data that is like sort of the largest in the population of data sets that we feed it. Does that
Interesting.
answer the
Thank you so
question better?
much.
Yeah,
Yes, thank you so much. And great talk. I really enjoyed the videos,
good.
especially.
Thank
Thank
you.
you.
It's
So
good to see
on
people,
your
even if I'm not actually seeing people's faces.
Yeah.
But I've worked with a lot of these people, and I know some of these people, so it's really nice to see everybody here.
this is great. On your theory of we just need better data to make better predictions, and you ended your talk with this plea for community sourcing of great data. Where are you looking to next? Like, where do you think yeah, where's the next expedition going and why?
Oh, Kelly Hogan is going to the other side of Greenland with a huge team this summer. Um, and nice to see you, Taryn. And so the great part about this is she reached out and we chatted about the challenges we had and like how we overcame them. And I had our drone people talk to her drone people, just trying to get it so that they can see our results and be like, oh, wow, we didn't know she saw my bed forms and was like, "Oh, that's just alias data." I was like, "There's some problem with your multi-beam." And I was like, "No, I think that's real." And so now she's going to go looking for those, right? So this is what I mean is like instead of holding dearly to your observations, like, and I can say this from the comfort of having tenure, but you know, I think the more we can share ideas, the more rapidly we can make progress on the science and demonstrate the need for some of these observations. Like just seeing the change over the course of a week was amazing, let alone like over the course of a season.
Awesome, thanks.
Yeah. What is the difference between geometry and dynamics? They go, I know. And so we talk about this a little bit in the papers. That there's some, I forget what the terminology is, but leakage. There's data leakage. So if we turn geometry off, certainly there's some knowledge of the geometry that's leaked into the other products. There's no way to legitimately turn it completely off, but this is sort of our approach, is acknowledging that that's as much as we could do.